going to talk to us about benefits of being aimless and the art of using good French loanwords.
All right, thank you very much. Lovely to see everyone here. I wanted to have a talk with this title for a very long time, but I have been denied this opportunity by my co-authors, but luckily the co-authors couldn't get the visa, so flâner is a verb in French, and it means to wander with no purpose. Okay, but the idea, the noun from this, the flâneur, it's not just the literal meaning of wandering with no purpose. There is a lot of kind of a idea, like 19th century wandering the French, Parisian streets ideas that I really want to capture. Right? So the flâneur is the man of leisure, the idler, the urban explorer, the connoisseur of the street. Okay, there is a lot of famous writing about the flâneur. For example, Balzac says that flânerie, the activity of flâneur, is gastronomy of the eye, this wonder and this sensing. It is the very opposite of doing nothing, right? It is not that you're like, whatever. No, it's a pastime and it's an activity to enjoy, to savor, to learn something, I love this one. There is no Anglo-Saxon counterpart to that especially Gallic individual, the deliberately aimless pedestrian, unencumbered by any obligation or sense of urgency. Right? This deliberately aimless. These two words are kind of in opposition to each other, right? But yet, it is this idea of trying to capture the world as it comes to you. Trying not to be busying off to do some task or another, but to accept the world in all of its fullness and to try to appreciate, learn, and become an expert in this world. And I think this is a very good thing to do for an individual when you're visiting in a new city. It's a wonderful thing to just walk around the streets aimlessly. I want to claim here that it's also a very good thing to do for our AI systems. And this talk is about trying to convince you that this deliberately aimless wandering turns out maybe is a good thing. Okay? Because what we do right now, well, we have Anglo-Saxons, we get to Paris, what do? We book one of those, hop on, hop off buses, right? And the bus brings you to Eiffel Tower. So boom, check, you got the Eiffel Tower. Then you go to the opera, okay, you saw the opera. Then you go to the Moulin Rouge, and then of course you have to go to the Notre Dame, but you can't even go to the Notre Dame because the buses cannot go there, so it's only from the side, right? Now you have seen all of the labels, all the Paris labels. You have done that, right? Now, have you learned anything about Paris? About Paris? No, you got all of the important bits. All the labeled stuff has been trained on, but you didn't get anything of value, anything of substance. You were just cooked up in this little bus, and you didn't really learn anything. I claim that a lot of what we do right now with direct supervision is this kind of going in a bus between the different places and not really learning anything in between. Here is one of my favorite examples. So let's say you want to do action recognition, popular topic. So you say you want to recognize opening fridge action. So you get yourself some data. This is from a data set by David Fouye called vlog. You got yourself a data, and you say, okay, here is your hand reaching out, opens the door, and sees some inside, then closes the door, right? You train your favorite 3D CNN mumbo jumbo. You train it on your labels, and you test it and get fantastic performance, 99.9%, right? And you're super happy you're submitting it to a CVPR. But if you actually wait a little bit and look, wait a minute, let's see what it's actually learning, right? And you look at where the classifier is actually getting excited about, where is it firing? And it turns out it doesn't care about your hand. It doesn't care about the fridge door. the only thing it really cares about is this frame with the open fridge texture, right? It doesn't even get, it's basically just this open fridge texture is such a iconic thing that it only needs to know that. And it can ignore all the rest. Now, is it doing anything wrong? No. This is the task you gave it. Your task is you had your whatever 30 or 300 actions, and this is only in one of those actions. So it's doing exactly what you told it to do. It's following your direction to the letter. It's just being a little bit wiser, and it's kind of taking a shortcut because you don't need to learn about the hand. You don't need to learn about the refrigerator. This is enough. And so it's doing absolutely the right thing, except that's really not what we want, because we wanted to actually understand the world. And so the argument that we wanted to bring here is that this is not an issue, not just an issue of data set bias. They say, well, you just get a bunch of negatives, so open fridges and then you can fit. No, you can do that, but there will always be something else that pops up. Our data is finite, so we'll never be able to clog all the holes. The problem here is that if you tell the computer what the task is that you want to do, well, it will optimize for that task. What we want to think is, how can we not have a task and see if we can get a more general agent, right? Because the problem we have right now is that all of our AI now is very specialist. It's either it's solving ImageNet and then it cannot do anything outside of that, or it's an assembly line that's screwing one particular screw in, cannot do anything else. What we are looking at is one to get some sort of a generalization behavior, kind of a generalist behavior where maybe you are not even the best at screwing that screw. Maybe you are not very good at doing ImageNet, but you can do so many other things all at the same time, right? So from class task specific, we want to generalize across tasks. From strong supervision, large data set, we want to have limited direct supervision and hopefully lots and lots of unsupervised stuff. From no adaptive train, you basically you have this training set, and then you have this testing set, and you train on the training set, and then you test on the next set. In the best case, some of the robotics people don't even do that, right? So this is already cool. But what we really want is to get rid of this whole test and training split. We want to just have online, as you go, lifelong learning. You just every data, it comes in, first it's your test set, and then immediately it becomes your training set. So you only test on one piece of data once, and then you just keep going on. And then you are not able to really overfit, because you never see that thing again. So what we try to do is to see if we can kind of move from the left side to the right side. And really this is, I'm just the mouthpiece. Most of this research has been done by our two wonderful students at Berkeley, Deepak Pathak and Pulkit Agrawal. Deepak is, it's actually, most of it is his slides, and he was supposed to be here, but he couldn't make it, and so you are stuck with me, okay? But please, these are the folks who are really in charge. So what we want to do is, let's think about actions. Let's think about your action is you're trying to type rope, for example. So you have your initial state, you have your goal state, you want to tie a knot, and you want to say, okay, what is the set of sequence of actions that I need to perform to go from the initial state to the target state, right? Well, what can you do? Well, one thing you can do is you can do imitation. So you can actually show the robot a sequence of actions, and once it records this, then it can do a kind of nearest neighbor to the next time, and it can actually repeat it, right? And this is fine. In a kind of a conveyor belt setting, that makes a lot of sense. But it's kind of tedious. It's specific to the one particular thing on the conveyor belt that you want the robot to do, and it's still you need to quite a bit of data to get it work. The other very appealing alternative is reinforcement learning, right? It's kind of like magic, right? So you don't need to do any hard work. You basically say, okay, I have my current state, I have my policy is producing action gets you somewhere else, and then at every point you're asking, do I get any reward for where I am right now, for this state? And once you end up at the goal state, then you get a reward, and then you kind of propagate it back, and you say, oh, okay, I need to get more of that reward, right? Sounds beautiful. But it's kind of hard on a real robot, because, think about it. The reward here, you really only get at the very end. Most of the time you get nothing. You get a 0. You only get like a +1 once you get to that final node that you wanted. And you initialize this randomly. So you're basically just wandering around aimlessly, hoping that you will, bump into the goal state. How likely is that to happen for something as complex as node time? Deepak estimates that it's going to take 10 million interactions. I don't know. I haven't tried. But it's a lot of work, and this is why it's hard to do on the real road, right? So what actually happens in practice is something maybe a little bit less glorious, less glamorous, right? Usually what happens, like the DeepMind famous work on Atari, you play the Atari games, but your reward you don't get it at the very end once you finish the game, like in Russell and Norvig textbook. Actually, you get it almost at every frame. You get the score, and you're trying to improve the score, right? So now your reward is nice and smooth, and so now you could actually, RL can actually do its job, right? And this is still very cool, but it's kind of hard to make this reward thing for practical tasks, even for simulation tasks, something like navigation, right? There isn't really, you have these apples that just happen to be there as these intermediate rewards, and without it, at least kind of classic RL, without any extra stuff, just cannot solve the problem without these, intermediate rewards, these apples. But the thing is, life does not give you apples, right? Life is, you're right here, you're a 5-year-old, you want to become a fighter pilot, you're right here. All right, this is your goal, 20 years into the future. Now, think about all those gradients you need to propagate back 20 years. About deciding, which toy to play with today so that you can become a fighter pilot 20 years later. This is talking about vanishing gradients. This is not going to work, right? It is fundamentally not going to work. And so, in fact, we humans don't do that. What we do is what the developmental psychologists call intrinsic motivation or curiosity. We just muck around, we play around with stuff, we don't really have any particular goals for a long time. We're just playing around and then hopefully learning skills that will eventually be useful to us in whatever task we decide to do 20 years down the line. Maybe they will be useful, maybe not, but on the whole, on average, should be useful. Okay? And so it's not just kids. Turns out this kind of distinction between a specialist and generalist exists in lower animals as well. The classic example from Alice and Gopnik is the chicken is your ultimate specialist. The chicken comes out of the egg, it's already pecking. It's ready to, and it continues pecking all of its life. Doesn't really do anything else, but it pecks from day one. On the other hand, the crow, same brain size, also a bird, right? It is one of the smartest animals on the planet. It is really, it can use tools. It can do really, really amazing stuff. But it's born. It can't do anything. The little baby Czech crow is completely helpless. It relies on parents to take care of it for a long time, bring it food and then take it to school, dress it up and all that stuff, right? Just like human babies, right? And in fact, the chicken just goes directly into this whole exploitation mode, whereas the crow has this preset period of childhood where you do nothing but explore, which is kind of a non-trivial thing if you think about it. Like you're not even kind of doing a little bit of book. No, you're just setting up this time to just explore and do nothing and be not productive and be a burden on your parents, with the hope that when you grow up, you'll be smart enough to do better evolutionarily than if you started from day one. Okay, and in fact, there is a very nice graph here, which is weaning time and days, basically length of your childhood, versus your IQ. Okay? And you can see that in the animal kingdom, there is a nice linear relationship. The longer you wean, the smarter as a species you are. Okay? So it suggests that this initial phase of exploration gets us to be doing fun, learning better things and being more smart later on in life. Okay? So this is basically our motivation. And so we thought, can we somehow use this kind of a goalless exploration, this Flâneur behavior, to get our agents to be smarter? Okay? And how do we even formulate this? So I'll show a few of the results here, and there's plenty of work that has been done in this area. There is an area of basically kind of a exploration by visitation counts. You remember where you have been, so you can try different things. And there is another direction which is basically predicting uncertainty, and this is roughly the area that we are going to talk about. But we are really trying to do it. Actually have some algorithms that actually try to run it in practice and see where it goes. The first thing we try to do is we try to say, okay, let's do it in simulation, but at least let's not write our own simulator. Let's use some other people's simulator. And he thought, okay, Mario Brothers sounds like a cool simulator. Let's see what we can do. Can we learn just from curiosity? What can we do in Mario Brothers world? So we start out. Our observation is the pixels of the game, and our actions are the keyboard, the arrow keys on the pad, right? No score, right? We don't know anything at all, nothing else. So what are we going to do? Well, our agent is going to be, the key thing about our agent is going to be predicting everything always. It's going to be this prediction machine. So it's going to say, okay, I'm going to try to see what happens if I take the left action, what happens if I take the right action, and it's always going to try to build a model to predict what's going to happen, right? And then the idea is that every time you're going to exercise an action, first you're going to think about it and make a prediction about it. So you're thinking, okay, I'm going to press the up key. And first you're going to say, okay, what would happen? And then you go, I think that's going to happen in your imagination, right? And then you actually do it, and then you see, so, oh, look at this, I was right. Right? And then it kind of boosts your prediction for that particular action. Okay? But that's not that much signal. What signal you get is when you're wrong. So here you're predicting that you're going to go up and come down, but actually you get stuck at the top of the spike. Okay? Now, this is actually a very useful signal because this means that our prediction failed. And so this is how the curiosity is defined in this case. Curiosity is a failure to predict. Okay, so that's our definition of curiosity. It's when you try to predict something and you fail to do it. You become more curious and you start. There's has a very strong connection to all of this, old good hard negative mining stuff, right? When you are not sure about something, you want to explore that more. That's just as simple as that, right? So the idea is you have this kind of loop where you train a model, you predict the consequences of its actions. If your prediction is good, that's great. If your prediction is bad, it increases your curiosity and forces you to go and evaluate that area again and see if you can get a better prediction. And so you basically have the two competing things. On one hand, you want to be a good predictor. On the other hand, you want to always be in a place where you're more curious, so your prediction is not going to be good. So you have these competing things, and you're fighting with them at the same time. So they're all both happening at the same time, and there is no training set or test set. It just always happens online as you go. Okay? So what does it mean in practice? So what we have is we have a current state. We can also have our policy network, just like RL, and then we could spit out an action, next state, and the main thing here is what's our reward. And the curiosity reward is basically we have a little curiosity module that produces a reward that we fit in kind of a standard RL setup. But what's the curiosity reward? The curiosity reward is basically failure to predict. So we need to now do the prediction. So we need an action, we have a current state, we need to predict what our model says is going to be the future, and we compare it with the actual next state. right? And if we didn't predict well, that's high curiosity. Just like Eric mentioned and a bunch of other people mentioned before, predicting in this kind of forward state, predicting pixels is very, very hard. You have multimodality, you have high dimensionality, so this is just very hard to do, right? So what can we do? Well, one thing to notice is that we don't need to predict everything. We don't need to deal with a lot of the multimodality, because when you are a little robot here, maybe you don't care about, you know, what this lady is doing here, right? Maybe really all you need to care about is the stuff that's directly applicable to you, the stuff that you can that can affect you and that you can affect. Okay, something like this. And so the idea then is to predict not in pixel space, but in some sort of a feature space. So now we have a feature space, and then we can do prediction in that feature space. And in that feature space, hopefully the feature space is low dimensional, it's easier to predict, all the nice things happen, right? Now the problem is that there is a trivial solution, of course. You could just have the feature space map everything to 0, and then everything is going to be great, and you're going to be predicting everything, and it will be fine, right? So what we need to do is we need to somehow train the feature space to have the features do the right thing. And so here we have a little bit of a self-supervised story where we have a little pretext task, and our pretext task is a little inverse model that takes the features of the current state and the next state, and it predicts what was the action that was taken to go from the current to the next. Okay? It's a completely useless task. We don't actually need it. But it's a nice pretext task because it will tell us how to, it will learn how to have features that work well here. And it's a task that's actually pretty easy to do because now you are in low dimension, you're predicting something that's very low dimensional, just a few actions. So now you don't need to worry about, are you using L1 or L2 or all that stuff, right? Predicting high dimensional things is hard. Predicting low dimensional things is easier. So you always want to be in a regime where you're predicting something low dimensional. And so here where this task is very easy, and what it does is it trains a feature for us that actually does pretty well, and then now you can actually use it in a curiosity reward. Just a little side note, in our latest paper we just posted on archive, it actually turns out that even something as simple as a random feature here also works okay in many of the cases. Not all, but many of the cases. So I think the idea of having a feature space that's not pixels, that is somehow low dimensional, is an important one. But if you want to actually do something in a very complex environment, that this kind of inverse training is actually very helpful. Okay, how much do I have? How much?
About 12 minutes.
Oh, okay, perfect. All right, so now we have this thing, we have our, we fit it as a reward, and now we have this kind of a Flâneur Mario brother guy, right? He doesn't have any objective, he doesn't have any external reward, he just wants to be curious. That's all he wants to do. No score, right? So how well does it do? So at the start of training, it basically just jumps around and doesn't do anything, right? But now, after a little bit of curiosity training, it basically starts moving. Because you can only move to the right in this game anyway, and you get bored staying around. So it's not going to go as well as if you actually have a goal. You're still kind of wandering around, but eventually you make progress. Okay, and so you can see that behaviors emerge. You're jumping enemies, you're jumping pipes, you're killing enemies, and interesting, you're staying alive, right? Which is again not something that we designed it for it to do. It just kind of comes out. The reason we think is in Bay Area we have this idea. It's called Fomo, the fear of missing out. If you go to San Jose area, you have to know this word, Fomo. It's basically Mario is having FOMO. He's worried about missing out on future curiosity. Like if he dies, he'll have to go back, and then he's going to be bored. He wants to go forward and be curious. And that seems to be enough to propel him to go forward. Maybe like the rest of us. Okay? So, of course, for us vision people, the important thing is not how it does on training set, but what can it do on a test set, right? So, we can train on one level, and then we can say, okay, are those behaviors generalizable? Can we apply what we learned, the policy, to a new level? And so here we're testing on a different level, and you can see that just out of the box, it's able to do stuff. It's, you know, it's the enemies are different, the geometry is different, but it's still able to do reasonably well. Okay. Now for level 2, not so well, because you can see the level 2 is very, very different, and so it doesn't really do much. But that's okay. We are vision people. We know how to fine tune, so we can do a little bit of fine tuning, and off we go. And now it's off to. And the interesting thing here is that so fine tuning is much better than not fine tuning, but it's also actually turns out to be better than training level 2 from scratch. Now, does anyone have an idea why that is?
You have already accumulated the knowledge you got from the level 1.
Yeah, but it's a different thing. You know, it's always better to train on the actual data you want to test in instead of some other thing, right?
Becomes more general.
Maybe. I think that a lot of it is because of the way that the game designers design these games.
It's easier.
They're actually expert curriculum designers. They basically teach you stuff in the first level that will be useful for you in the second level, etc., etc. Because the game designers are really in there to make sure that you can play the game without reading the manual. You don't need to know what the goals are, the goal states are. You just want to basically enjoy the game just by being curious. So in this case, actually using games was a particularly good choice because they're designed specifically to promote curious agents. And this is kind of an interesting example here. Okay? And then of course we can do it for 3D navigation too. So here is curiosity, and this is just random exploration, and you can see that it often gets stuck. And you can train on one map and test on a different one, and it's still able to navigate on a new test map. And so, yeah, so you generalize the new scenarios. It doesn't get bothered by random pixels, so it doesn't get stuck if you have a bunch of random pixels, so that's good. And then, a lot of the robotics people was like, well, Mario is fine, Doom is fine, but you should show it on many other things. And so in the latest paper, we just said, okay, fine, we're just going to write it on all of the Atari games and other stuff as well. And it's kind of weird that, it actually, without any notion of what the rewards are, it can do surprisingly well on a lot of the Atari games. Which again suggests that probably the designers of the games were very aware of the fact that you want to make this curiosity behavior, elicit curiosity behavior in your players so that they enjoy the game. So that the curiosity behavior aligns with the goals of the game. Right? It's all about alignment of behaviors that is kind of an interesting thing. And it's not just game designers. If you're designing parks, for example, or Disneyland or something like this, there is a lot of places where you want to lead your agents and explore the environment. And I think this is an interesting direction. Now, the other cool thing we can do is we can put two curiosity agents fighting against each other. And here, this thing basically never drops the ball. It doesn't get many points, but it's enjoying the rally. It's having fun because that's the curious thing to do. It kind of learns how to walk in this walking thing just by being curious. And the only thing it gets stuck on is if it sees TV. Now, if it just sees a TV, it ignores it because it's not in the feature. It's not in the feature. But if you give it TV and a remote control, that's it. It's stuck. It's not going to move. So having a TV in the home is fine. Just don't give your kids the remote. Okay. So how much time do we have? 5. Okay, good. So now this is a little baby crow chick, and it's been exploring and learning skills, but not really doing any goals. Now it has grown up, and there are now actually some goals. So can we actually use this learned thing for actual goals. So here, there's a couple of things we can do. One thing is we can just take this thing and then run it with not just curiosity but an external goal at the same time. And we can do that. For example, we can do all of these kind of navigation things when we can restart from a different place and try to find the goal. And now you have a reward, but it's very sparse reward, and you can see that curiosity does much better than the competing methods. It gets the reward much faster because it has this. It's shaping the reward function with the curiosity reward, which is dense. And you can again transfer to a new map, and it still does okay. So you can have here kind of a our thing versus a vanilla RL, and the vanilla RL doesn't do anything, and we are okay. Okay, but this is lots and lots of samples, not something you can do on a real robot, right? That's the problem, and so the second thing that we looked at for actually trying to do it on a real robot is visual imitation. So we can now look at some. I know I thought I would never say this, but supervision, yes. But it's a supervision of a very weak. What you're just showing one demonstration, just one. And we're not going to train on it, right? This is going to be a test time. So, no overfitting. We're just doing it at test time, okay? We're going to explore the environment. We're going to distill the exploration into skills. Now, this is going to all happen at training time. Now, at test time, only at test time, we actually get to see the goal. We get to see the task much, much later. And then we say, okay, can you use everything you learned to do well on this goal? Okay? So basically it's kind of the similar story but on a real robot. So we have a couple of real robots here, and we basically learned these tuples of what happens, state, action, and what's next state. State, action, next state. We just explored this space here for navigation, for rope, and learn a lot of this data, and then try to distill this data into a model. And again, there's kind of a couple of ways you can do it. You can do a format dynamics where you predict next state, but as we said, predicting pixels we don't want. So here we're actually going to do the inverse. We're going to predict actions and learn a model that predicts actions. And I'm going to skip a whole bunch of details here on learning these policies. And then at test time, now you say, okay, here is the goal. Given the current state, this is the goal state, this is the goal image. Just given one image, make it happen, right? And now it's not that easy because some of those things are kind of hard. So you might actually need to give it a few images, kind of intermediate step of your demonstration, but not that many. Okay, and then let's see if it works. So this is a demonstration, and now, okay, it's your turn, Mr. Robot. Do. And of course, all the bad things apply, just like Abhinav says. The green cloth, the same, all of these things apply. But because we don't actually train on the task, the hope is that we can actually avoid some of the really obnoxious overfitting. It's still there is overfitting, but at least maybe better than before. And there is the navigation example. Here is the robot walking around, and then at test time, there's the current image, and this is your goal image. I'm not sure I understand why anyone would want to do this task, but again, the robotics people are very excited about it. Oh, look, I found that image. I think I can do it with descriptors too, but whatever, we can also do it here. Okay, here we go. We got the image that you already had to begin with, so you didn't really need to find it. Whatever. And finally, I wanted to have a little plug for another paper, which is, I'm very proud of this paper. It's an ICML paper, ICML oral, with basically no computational thing at all. This is basically like a user study, okay? And the argument is, RL is very sample inefficient. That's why it's hard to do in a real robot, because there is a lot of samples you need to run. And so a lot of it is because we don't know what we're doing. But some of it is also because the agent comes to the task tabula rasa. But humans, even if you never played video games before, you look at this video game and you say, well, I know a lot of stuff. I have, I know that this is probably me. I know that these things are probably enemies. This is probably bad. This is probably good, right? There's a lot of information. And so the argument is, what happens to humans if we screw over with this kind of prior information? So we took this game and we just re-rendered it with different textures. And we put it on mechanical Turk. And the users were so unhappy with us. They were not happy. There was a lot of shouting on the comment section. They did the normal game you can do it in a month. Oh, sorry, in less than a minute. This thing was like 20 minutes for the few of them who finished. It was like 20 minutes. It makes the game much harder. For Unreal, of course, it doesn't matter. It doesn't see the difference, right? They're all the same. But for humans, it was a huge difference. And so the argument here is that, yes, sample inefficiency is an issue, but also the fact that we need the lifelong learning. We shouldn't be starting things from scratch every time. We need to use what we have seen before. Okay? And blah 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 data. Anyway, thank you very much, and all praise to Deepak, who is actually should have been here. But thank you.
Questions?
Yeah, so in traditional RL, let's say for navigation problems, even if they're able to solve it, and let's say they're trying to go down a hallway straight, like even in the earlier example you showed, it was still like very jaggedy, very choppy, like left, right, left, right, left, right. And even with the curiosity approach, it was still a little bit left, right, left, right, left, right. So like, how do you kind of learn with this curiosity model a little bit more stably? Or is that just regularization?
Well, I think that's a good lead question, because the idea about a Flâneur walking down a Parisian street, he's not going to walk in a straight line. He's not, I'm rushing for the metro. He's going to look around in the street windows. He's going to be in a little jaggy way, because he's always exploring, as he's exploiting. There's always you can never know what happens if you take a step to the left or a step to the right. So I think this is actually a normal behavior if you're in this kind of lifelong scenario. Now, if you're really only exploiting, then yeah, you should just go and then just set your external reward high and then you just go, right? But in normal circumstances, it's good to, smell the roses, basically.
So you went from taking a tour bus in a beautiful open world to being a Flâneur in like this toyish little video game.
Yeah.
Many
toyish video games.
Many toyish video games.
54 many toyish.
Yeah. Any idea how to be a Flâneur in the real world?
Yes. Very, very fair. Basically, the idea was that I'm too cheap to have robots, so Deepak went to hang out with Abhinav for the summer and play around with Abhinav's robots to try to do it in the real world. And I think it's hard. Fundamental problem is that in this world, and also in the world of simulations or even like Google Street View, it's nice for us because the space of actions is actually quite small. There is not that many things that you can do. In the real world, the space of actions becomes much, much bigger. And now this whole thing about predicting actions is not so unimodal, it's not so nice anymore. So I think that's kind of one of the fundamental things. That's the big open challenge to push it to maybe even I will be okay with even a slightly bigger world. Yeah.
Okay, I think the story is really good, but it seems untrue because if you look at the baby, it doesn't seem to be doing like aimlessly. I mean, it always builds this block tower. It doesn't seem, if it was aimless, it will be impossible. Like, I mean, the babies seem to be having some kind of goal in their minds while they are building whatever videos you are showing. So this whole aimless story, it seems to be nice, but
I think it all works out if you think about it hierarchically. So instead of in a flat curiosity, you're completely right. Why would it ever build a tower? But in a hierarchical curiosity, now you want to know what happens if I know how to do this, right? So I would just stop here. But then I want to become curious about what happens if I keep piling and piling and piling and piling, and what happens if I pile something like this high, right? And to do that, now you have like a mini sub goal, and then you actually you're doing the. So I think hierarchy is the right way to solve this problem. But that's again my intuition, and yeah.
But to add to this, I mean, it's not the baby that's curious initially, it's the parent who shows the baby the new thing. It's not necessarily that the baby just goes and stacks blocks, it's the parent who shows it that if you can put a block on top of that, you can put another block of that, and then maybe you push it and it falls over.
Okay, Philip, I know that you as a young parent feel that you are super important, and that without you, the baby would just never learn anything. But unfortunately, that's not quite true. Yes, parents help a little bit, but 90% of learning happens without any supervision, according to Alison Gopnik at least. There is a little tiny sprinkle of supervision once in a while, and you're doing a great job at that. But a lot of it happens without supervision. Just you're not there to see it.
Okay, one or two more questions. So.
So basically, you mentioned like aimless exploration and building upon the previous question. So in most of these setups, like the implicit aim or like implicit goal is to survive, right? So like most of like
there is no such goal.
But like most of the games like Mario or all of I guess most of the Atari games, you want to survive, and that's like implicitly encoded in the game. So you
True. Although that's not actually how you get the most points. If you just survive, your point count is going to be kind of low. So, but yeah, there is this implicit thing, yeah.
Yeah, so when you're, I mean, this whole architecture design of like predicting actions or exploring is basically exploring to survive. Like even you mentioned that it's like staying alive, kind of emergent behavior. So yeah, I'm just saying it's like not totally aimless, right?
Well, but the survival thing is never encoded. It's never coded in. It emerges. In the same way, I was just reading, Darwin, and it's actually, there is some evidence that like death is actually an emergent property. We don't have to die. It just works out that way. It's better for evolution that way. So it improves generalization to have this bottleneck. But other than that, we don't need to do it. So yeah, I enjoy thinking about these questions, but yeah, I'm not sure. Maybe it's not that relevant. Yeah.
Last question.
Actually, my question is quite similar, because when you take out the reward, then you learn to survive, but you never reach the state when you finish the stage in Mario, for example, like going into this last fight.
Oh no, but this one, this video, look at this. It finishes like 12 levels, I think. It's fine. It gets there.
There is no reward actually.
Yeah,
you can
there is no reward.
In the stage and stay. It will take.
It just gets bored and wants to move on.
Okay.
Yeah, that's. I mean, that's how I operate too. So I have an affinity for this Mario here. It makes total sense to me. I'm not looking for those gold coins, but I just get bored, so I just need to move on. All right.
Okay, I think we will end here, and sort of you can ask your question offline. Let's thank all your